In this video, we're going to practice finding critical numbers of functions. And critical numbers, just as a quick recap, critical numbers are places in the domain of our function where either f prime is equal to 0 or where f prime does not exist. But the important thing is that these must be in the domain of f of x, meaning if a number is not in the domain of f of x, it can't be a critical number. And we'll see an example of that coming up here in just a minute. So if I'm looking at this first example, it just says find the critical numbers of f of x equals 1 minus x cubed. Well, if I want to find critical numbers, first thing I might want to think about is the domain of this particular function. If I wanted to kind of pull this to the side and say the domain of f of x, we want to think about what type of function it is that we're dealing with. And in this case, f of x, this is just a polynomial. Polynomials, we know, have domain negative infinity to positive infinity, which essentially means there's not going to be any restrictions on our critical numbers. So for the most part, we're not going to have to worry about the domain. So for this problem, we can just focus on finding where our derivative is equal to 0 and where our derivative does not exist. So first thing I got to do is find my derivative. So first thing I got to do is find f prime of x. Here I can just use my power rule, and I should have f prime of x equals negative 3x squared. So here's my derivative. And I like to consider each of these two cases separately, places where the derivative is 0 and places where the derivative does not exist. So underneath that, I'm going to say, all right, well, let's find places where f prime of x is equal to 0. So I'll take negative 3x squared, set it equal to 0, and then we'll solve this equation for x. So here in this problem, we can divide both sides by negative 3. We'll have x squared equals 0. And if I take the square root of each side, I end up with x equals 0. What I need to check is this number in the domain of my function? Now, we said the domain was negative infinity to positive infinity. That's all real numbers. So that means that, yes, x equals 0 is a critical number. So that's good. The other case that we need to consider is places where our derivative does not exist, or places where it is undefined. Now, in general, the things that we're looking for when we're thinking about this is we're thinking about things like dividing by 0, square roots of negative numbers, and logarithms of non-positive numbers. I can look at the derivative that I found, and I can say, well, you know what, just by looking at this, f prime is a polynomial. And well, we just said polynomials exist everywhere, so that means that f prime exists everywhere. So that means when I'm thinking about places where f prime does not exist, there are none, because f prime is a polynomial. So if you find a derivative and that derivative is a polynomial, we don't need to consider this case because that function exists everywhere. It's defined everywhere. So there's not going to be any extra critical numbers there. So that means that we only have the one critical number here. We've got x equals 0. So there is our first example. Let's look at one more here. Here I want to, again, find the critical numbers. Here I've got a slightly more complex function. I've got x squared plus 4 over x squared minus 4. Again, before I do anything else, I'd want to think about the domain of this function g of x. And in this case, I am going to have a little bit more of a problem because I don't have a polynomial. I've got a rational function, and in a rational function, I'm going to be worried about where is the denominator equal to 0. So first thing I'm going to do is just kind of pull that off, and I'm going to say, well, what if we take that denominator, x squared minus 4, and set it equal to 0? I know that those are going to be x values that are going to cause problems for me. So here we can either factor or solve using square roots. I'll use square roots because it's pretty quick. X squared equals 4. And then if we take the square root of each side, we actually end up with x equals plus and minus 2. We end up with a positive 2 and a negative 2, which means for us, if we were to take x equals positive or negative 2 and plug that back into our function, we would end up with 0 in our denominator, and we can't divide by 0. So that means that this plus and minus 2, those cannot be included in my domain. Those are not a part of my domain. So that means when I think about the domain of f of x, I need to exclude those numbers. It's everything except for positive 2 and negative 2. So when I come up with a domain here, I would say, okay, well, it's negative infinity to negative 2, negative 2 to positive 2, and positive 2 to positive infinity. So this is the domain of my function. Negative 2 to positive, excuse me, negative infinity to negative 2, negative 2 to positive 2, and positive 2 to positive infinity. What this also means for me later on in the problem is that these two numbers, negative 2 and positive 2, cannot be critical numbers because they don't live in the domain of our function. So that's just kind of the first step that we've got to do. The next step is, okay, well, let's find places where g prime is equal to 0 and places where g prime does not exist. So in this case, we're going to have to use the quotient rule. So let's see, low, that'll be x squared minus 4, d high, derivative of my numerator is 2x, minus high, x squared plus 4, d low, derivative of our denominator is 2x, square the bottom, x squared minus 4, quantity squared, and away we go. So here's my derivative. I'm going to simplify this before I do anything with it. So here I would take 2x, let's distribute that. So let's see, I'll have 2x to the third power minus 8x minus, over here, be careful with these parentheses. I'm going to distribute the 2x first. So that'll be 2x cubed plus 8x. Denominator we don't need to simplify, so we'll leave that as x squared minus 4 quantity squared. And then I'm just going to distribute that negative sign so that it makes it easier to combine my like terms. And then I see, well, I've got a 2x cubed plus negative 2x cubed. Those two will cancel. And then I'm left with negative 8x plus negative 8x. That'll be negative 16x divided by x squared minus 4 quantity squared. So here's our derivative g prime of x. We want to make sure we don't forget our derivative rules. We will still need to be using those here in this new chapter. So this is my derivative. I want to now think about places where that derivative is either equal to 0 or places where that derivative does not exist. So if I think about places where the derivative is equal to 0, we'll start on this left-hand side here. I'm just going to take my function that I found and set it equal to 0. So negative 16x divided by x squared minus 4 quantity squared is equal to 0. So I'm going to multiply both sides by my denominator, x squared minus 4 quantity squared and x squared minus 4 quantity squared. On the left-hand side, those two should cancel, leaving me with just negative 16x. And on the right-hand side, 0 times anything, well, that should just be 0. So let's see, negative 16x equals 0. We'll divide by negative 16, and I end up with x equals 0. So this is a potential critical number. I did have some problems with my domain, though, so I need to check and make sure that 0 is in my domain. Does it live in the domain of the function? Well, we said our domain here was negative infinity to negative 2, negative 2 to positive 2, and positive 2 to positive infinity. Essentially, remember we said everything except for negative 2 and positive 2. Well, 0 is not negative 2, and it's not positive 2, so that means that x equals 0 is going to go ahead and be a critical number. So now I need to think about places where the first derivative does not exist. The thing I'm worried about, again, I've got this rational function. I'm worried about that denominator being 0. So I'm going to take that denominator, x squared minus 4 quantity squared, set it equal to 0, and we'll solve for x. So let's see, I can start by taking the square root of each side. On the left-hand side, I just end up with x squared minus 4. And on the right-hand side, the square root of 0 would be 0. So again, we can solve this using square roots one more time. X squared equals 4. And then I end up with x equals plus and minus 2 once more. Hopefully that kind of rings a bell for you. So x equals plus minus 2, they might be critical numbers. I need to check and make sure that they're in the domain of my function, though. If I go back up, we had a problem here at -2 and at +2. Those are not included in those intervals that I wrote. We said that the function is undefined at those intervals, which means that these are not critical numbers. Now, that doesn't necessarily mean that they're not important. If I wanted to say, find where my function is increasing or decreasing, I would actually still include those on my number line. I would say, okay, here's -2, here's 0, here's +2, and I would set this problem up similar to the one that we did, the very first video that we looked at. But they are not critical numbers, and that's important because critical numbers is kind of a spoiler for the next section. Critical numbers are places where we can have local minimum or local maximum values. And if something is not a critical number, then it can't be a minimum or a maximum. So it's not a critical number. Instead, if you wanted to call these something, they are partition numbers, which are still important. There's still places where our first derivative could change sign, but they are not going to be local minimum or local maximum values, which is something that we're going to talk about in the next page.